you are all aware of the fact that I have already completed the principles of thermodynamics more or less in details. Today and today onwards, I try to give an application of the thermodynamics in two-phase equilibrium and general phase equilibrium. Before going to that chapter, two chapters, let me first define the solution and its concentration, and it is the lecture number 1. The solution is a homogeneous mixture of more than one substances, and the substances remain in solutions as non-reacting. And you can say the solution homogeneous. By means of homogeneous, we mean that every part of that solution, the properties will be uniform and these substances are distributed thoroughly throughout the whole solutions. And we shall rather confine our discussion as required in the case of this two-phase equilibrium. The two component or two substances are being mixed up homogeneously, and it is called binary solutions. And the solubility or the relative proportion of the two components in these solutions will range up to certain limit, up to the saturation limit of the solutions. And thus a solution we shall restrict a binary solutions, and binary solutions may be defined as solution is equal to solvent 1 plus a solute, and it is 2. Means every property associated with the solvent will be given by the subscript 1, and for the solute with the subscript 2 in the whole chapter of this two-phase equilibrium. And the solvent means that component which dissolves, and solute is the component which is dissolved, or whether it is present in large amount, and this solute is present in small amount. However, suppose if we consider the 30% alcohol in water, then water is present 70% and alcohol is 30%, so alcohol is solute and water is a solvent. But there might be some exception. Exception is that if we consider the 60% sugar plus 40% water, forming a syrupy sugar syrup. In this case, though it is present in large amount in the sugar syrup, but it is not this solvent. Solvent, the one criteria for the solvent is that solvent will remain in the same state, same physical state as the solutions. Since it is the liquid state, physical state is liquid or the liquid phase, and water is in liquid phase, so the water will be the solvent and sugar is solute, though it is usually taken as exception. The concentration now, the relative amount of this solvent and solute are expressed by means of the concentrations, and the mode of expression of the concentrations are of various types. Concentration is a important yardstick to define the state of this solution. The state of the solution is defined by temperature, pressure and the concentration. If the solution is having a particular temperature, particular pressure and particular concentration, then all the properties of the solutions will remain same so long these three properties will also remain fixed. So the concentration, define modes of concentration. First mode, very simple one, percentage, and it is given this symbol like this. Percentage means it is the parts of this solute dissolved in 100 parts of this solution. So this is the percentage. Suppose if we consider the 3%, means that 3 parts of this solute is dissolved in 100 parts of this solutions. And this percentage will be of different type, and first type is the mass percent. Mass percent, m by m and percent, and it is defined as m2 divided by m1 plus m2 into 100. It means that m1 is the mass of this solvent, m2 is the mass of this solute, and this m2 is the amount, this is the part of this solute in 100 parts of these solutions. And this concept, this mass percent is temperature independent. Temperature independent, and this mass percent is usually used when both the solvent and solute are taken the solid. As for this alloy, say zinc in copper, zinc is dissolved in copper forming a solid solution. So second one, volume percent. Volume percent, V by V, and this is percent. And it is defined as V2 divided by V into 100. V2 is the volume of this solute, and V is the total volume of the solution, and it is multiplied by 100, giving you the volume percent. Suppose if we consider the 3% volume by volume alcohol in water, it means that 3 cc of this alcohol is dissolved in 100 cc of this solution, and this volume percent is temperature dependent. As temperature is changed, the volume is also changed. This is usually taken when both the solvent and solute are in liquid state, say alcohol in water, or say acetone in water, and so on. And this third one, mass volume percent. Mass by volume percent. And suppose here it is represented as M2 divided by V into 100. Say M2 mass of this solute is dissolved in V volume of the solution, and it is to be multiplied by 100. This will be the mass volume percent. It is generally used when the solvent is liquid and solute is solid. say 3%, if we consider the 3% urea in water, mass by volume, then 3 gram of urea is dissolved in 100 cc of these solutions, and this one is a temperature. This one is also temperature dependent. But these are normal mode of concentrations. Most important unit of concentration is molarity. And it is 2. Molarity symbolized by N, and this is equal to, this is defined as N2 divided by V, where N2 moles of solute is dissolved in V liter of this solution. It is to be remembered that it is solution and V liter. So this concentration is widely used for the preparation of the solution in laboratory use. Though it is not very accurate, as a temperature, it is temperature dependent. As the temperature is increased, V is also increased, and thus N2 by V is decreased. Suppose you are preparing today at 25 degrees centigrade the 0.01 mole urea solution in water in your laboratory, and tomorrow you see the temperature is raised to say 30 degrees centigrade. So these solutions will then at 30 degrees centigrade will no longer be 0.1 molar, it will be less than 0.1 molar concentrations. Though it is temperature dependent, but it is widely used in laboratory purposes due to simplicity or easy with which this molarity solution could be prepared. Say if we like to prepare say 100 ml of 0.1 urea solution in water. Very simple to prepare these solutions. We have to take a long neck volumetric flask. There are so many volumetric flasks ranging this 50 cc, 50 ml, 100 ml, 250 ml, 500 ml, or 1000 ml, etc. These are the type of volumetric flasks used in this laboratory. So suppose we like to 100 ml of 0.1 molar urea solution in water. In this case, the long neck, here is a cut mark, and there is a funnel to be set up, and temperature is written as generally 20 degrees centigrade. And for 100 ml 0.1 molar urea solutions, we have urea to be required. Urea is required that 0.1 into 60. 60 is the molar mass of this urea divided by 100 and into 1000 divided by 1000 into 100 is equal to 0.6 gram. So 6 gram of urea is to be taken and to be dissolved in 100 ml of water, 100 ml of the solutions. So this this amount of this urea is taken by weight in a chemical balance and give it in funnel, and water is added and stirred, and since water is the what meniscus of this water is curved surface, so this curved marker to be a tangent of this apex of this meniscus, solution meniscus. So these solutions will be 100 ml of 0.1 molar urea solution in water at 20 degrees centigrade. So this is very easy to prepare in this laboratory. And the third one, molality. Molality, small m. It is N2 divided by N. It is N2 divided by N. Where N2 moles of solute is dissolved in 8 kg of solvent. 10 kg of the solvent. So here lies the difference. It is the V liter of the solution. Here 10 kg of this solvent. Here lies the difference. So this one molarity is rather more accurate than molarity, and it is the temperature independent. As both are mass independent. There will be no temperature effect. So this molarity is used to study the properties where the temperature change occurs. Suppose elevation of boiling point and depression of freezing point. For this case, the temperature variation occurs, and for the temperature variation, the constant remains fixed. And the fourth one, the mole fraction. Mole fraction is given as symbol x. Suppose x2, x1 mole fraction of the solvent equal to N1 divided by N1 plus N2. And similarly, x2 mole fraction of the solute is N2, mole number of the solute divided by N1 plus N2. And naturally, you can see this x1 plus x2 is equal to 1. So if we know 1, then other could be calculated from this relations. So this mole fraction is very useful concentration terms, and it is required for theoretical investigation of the solutions. And this, whenever several substances are forming these solutions, in that case, say x1 equal to N1 divided by summation of Ni, ranging from 1 to 3 depending on the number of substances present in these solutions. Or better, Xi, mole fraction of this ith component, equal to Ni, mole number of this ith component, divided by total number of moles present in the solutions. So these are all about this mole fraction is also temperature independent. Mole fraction is also temperature independent, and the range of x1 is suppose 0 and 1. When x1 equal to 0 means only solvent is absent in the solutions pure. When x1 equal to 0 means it is the only solute and x1 equal to 1, then only solvent, no solid, only solvent. So for in case of the solutions, x1 is having the range from 0 to 1. As two components, solute and solvent, both are present in the solutions. So the value of x will be a fraction, means greater than 0 and less than 1. You can also have an idea about the interrelations of these mainly these three concentration curves. Suppose if we like to have an interrelations between the molality and mole fraction, then it could be easily have a relations between the two. A molar solution means a moles of the solute is dissolved in 1000 gram of the solvent. And suppose so x2 mole fraction of this solute will be equal to m. This is the number of moles of the solute divided by m, number of moles of the solute, plus 1000 gram of the solvent, and divided by its molar mass of this solvent. So this will be the relationship between the mole fraction and the molality of this same solution. Same one is the molecular weight or the molar mass of this solvent. And you can see whenever the solution is dilute, in that case the 1000 by m1 much greater than m. So in that case x2 would be written as m1 divided by 1000 and into m, or you can say x2 is proportional to m for a given solvent. Again we can find the interrelation between the three, this molarity and mole fraction. Suppose we have 0.1 molar urea solution in water, and density. Let us have one solution, 0.1 molar urea solution in water, and this molar solution is to be expressed in terms of this molality and the mole fraction. Density of this solution is 1.0542 gram per cc. So it is 0.1 molar urea solution in water means 0.1 mole of urea is dissolved in 1000 cc of the solutions. So 1000 cc, so mass of this solution is 1000 cc. This is the volume of the solution multiplied by the density and gives you the 1054.2 gram. And so mass of this solvent is this is the mass of this solution, minus the mass of the solute to be deducted here. Mass of this solute 0.1 mole means 0.1 into 60. 60 is the molar mass of this urea. So 0.1 into 60 means 6 gram is to be deducted from this total mass of this solution. So it will be, the mass of this solvent will be 1048.2 gram. So the molality of the solution will be 0.1, and this much mole of this solute dissolved in
1058.2 gram of the solvent and multiplied by 1000. So this will give you 0.095 molar solutions. So this 0.1 molar urea solution is equal to 0.095 molar solutions. And if we like to get this mole fraction x2 will be equal to this is the mole of this number of moles of this solute divided by number of moles of this solute and the mole of the solvent, and the solvent number of moles of this solvent is equal to 1048.2 divided by 18. 18 is the molar mass of water. So this will give you 0.0017. So this will be the mole fraction, this will be the molality of the solution, which is 0.1 molar urea solution. That's all about the solution and its concentration, different type of solutions, and different type of concentrations of the solutions, and some merits and demerits of different units of these solutions are described here. So thank you all who are watching this video, and please subscribe if you like this video. In my next class I shall try to explain the Raoult's law of evaporation, which will come to the thermodynamics of two-phase equilibrium chapter. Thank you all.